Okay, everybody, I'd like to welcome you all to the reinstatement of our CPSH seminar series. We have been virtual for the past couple of years, and now we are back live and in person and hybrid. So welcome to everybody in the room, welcome to everybody online. We're going to be doing these seminars basically on the second and fourth Mondays of every month. And then on the third Monday, we will be having just a general meeting of CPSH, which I guess we could also do in person in this room. We have this room every Monday from 1 to 2. Yep. So I'd like to welcome you to come back next week and join us for the CPSH just general meeting. And then on the first Monday, the executive committee will be meeting on from 1 to 2. Yep. And then on fifth Mondays, yes, we will do a social gathering somewhere. A lot of you were at our meeting a couple of weeks ago up at Black Star Co-op, and I think that was quite successful. And the center will spring for some eats, and all of you can then go in and buy your own libations as you wish. Okay, so I will now turn it over to Tim, who will introduce our first speaker.
Great. So yeah, I want to make sure everyone can hear me. If you just give a thumbs up. Yeah. Okay. So thanks everyone for tuning in. This is our first in a series of talk presentations we're going to have from recipients of the CPSH Student Research Awards in Planetary Habitability. So we awarded a handful of these last year to support student research in sort of the realms of scientific interest for CPSH. And so this is our chance to hear what these graduate students have been up to using this support. And so we'll have 3 of these talks this fall, and then probably another set in the spring. So it'll be really great to hear what all the students have been up to. And so each of these pretty much will have 2 speakers. And so our first speaker today is Dr. Kat Ross, who's a geo and thermochronologist who studies punctuated events in Earth's history, such as impact cratering events, which is what we're going to be hearing about today. Kat received her bachelor's and master's from McGill University in Montreal, Canada, and then recently defended her dissertation here at UT Austin this past summer. She's currently a visiting assistant professor of practice in the Department of Geological Sciences at UT, and then will start a postdoctoral fellowship at University of Wisconsin-Madison in early 2023. And Kat is going to be talking to us today about her research impact crater thermochronometry and the effects of shock microstructures. So take it away, Kat.
Thank you so much for the introduction. I'm going to do some screen cleaning here. All right, so hopefully everyone can hear and see me well enough. So I'm going to be discussing one of the chapters of my PhD research today. This was funded or have gotten samples from all of these different institutions, but as Tim mentioned, I'd like to thank CPSH specifically for funding part of this research, allowing me to focus in on some of this research. And then I also just like to thank my collaborators on this project. So impact craters are important because they are a ubiquitous process on rocky planetary bodies. They are thought to have formed the moon, resurfaced planets, and influenced the habitability of early Earth. So we have all of these craters here on Earth, colored by their age. Over half of these craters are only stratigraphically constrained. So that means less than half of the craters on Earth have a radiometric age associated with them, and less than half of those are regarded as precise. We want precise ages for impact craters because this is how we link to planet-wide events. So such as solar system events like a chondrite breakup that happened in the Ordovician, global mass extinctions such as the day the dinosaurs died, the Cretaceous-Paleogene boundary after the Chicxulub impact, or climatic changes. So changes in glaciation patterns in early Earth, such as in this crater in Australia. So there's a couple of ways we date impact craters. So the sort of gold standard is using a mineral called zircon, using the decay of uranium to lead. And you can see here, this is an example from the Chesapeake Bay impact structure, that the age is recorded here. So this is sort of our gold standard. This is a good chronometer that we use. However, sometimes these grains are hard to find. We can also use argon-argon dating to date these craters. So that's shown here. However, this one will give a so-so rating because melt, which we use to date these craters using argon-argon, can be hydrothermally altered or not preserved or eroded away from these structures. So sometimes we don't have any material to actually use for this. And the thermochronometer that I'll be talking about today is using the mineral zircon, but using the uranium, thorium, helium thermochronometer. And this is very useful on lithologies that are not melt. So you can use it on granites and basement rocks that are preserved within the impact craters. And you can use it on smaller structures. But what you'll see here, I'll start to point out, is that the uranium, thorium, helium age, which I'll call the zircon helium age, is younger than the uranium lead age. Another interesting tidbit of information to keep in mind is that you can reset or change the age to the impact age in a matter of less than a second if the temperatures are high enough. And if they're around 300 degrees, you can reset to the impact age at a couple of thousand years. So zircon helium has been done in impact craters before, about 13 worldwide. I've normalized this y-axis to previous workers, uranium lead or argon-argon age. And again, what I'll point out is that the zircon helium age is younger than the other ages that we see in most of these craters, including the Reese crater here, which is about 14.8, and I'll discuss this crater in detail later. So we have to come up with some reason, or why are these ages younger than some of our other thermo and geochronometers? Zircon is a pretty hefty, robust, durable mineral, but with the pressure and temperature conditions within an impact, you can create damage and deformation within a single crystal. So this damage and deformation likely influences how helium, or the daughter product of our thermochronometer, diffuses through the grain, so how it escapes and actually gives us our age. So this is actually probably going to affect how robust our age is. If we want to date impacts, we need to know what we're actually dating, right? So the goal of this project is to assess the microstructures, characterize the microstructures, and then assess how they influence the diffusion kinetics and then the age that we're getting. So to do this, we're going to look at two separate craters. The Chicxulub impact crater in Mexico, which I briefly mentioned before, it's related to the mass extinction, including the dinosaurs, and the Reese crater in Germany. So there's a couple of differences between the craters, which is why we wanted to use two. So we have the Chicxulub, which is 66 million years old. It's got a hydrothermal system that could last up to 6 million years. That's a new result from argon-argon from some of our collaborators. It's a large crater. It's 200 kilometers in diameter, has mixed target rock. The Reese is much younger. It's 14.8 million years old. Its hydrothermal system could be about 0.7 million years long. This is ongoing work that needs refinement, so we can definitely help out with that with this new chronometer. And then it's a smaller crater, about 25 kilometers across, and also a mixed target rock. I'll just point out the zircon helium ages that have been done here on UT's campus by fellow CPSH member Connie Rasmussen, and some older data from the Reese. And you can see that it's younger than the argon-argon impact ages. So if we look a little bit more into why we care about this age, we can think about the hydrothermal system longevity. Impact craters are a great source of heat, fluids. They've got an elevated geothermal gradient. You can have energy stored within the structural highs within the crater. You can get these circulation patterns within those structural highs, and you have these impact melts and breccias that are a good source for these hydrothermal systems. And so these are often habitats or even cradles of life. So the optimal conditions for hyperthermophilic and thermophilic life are 50 to 80 degrees and above, respectively. An important thing to note here is that cooling to these thermophilic and hyperthermophilic temperatures depends on the size of the crater. For smaller craters, it's a couple of thousand years. And for larger craters such as Sudbury, it's a couple of million. In the case of the Chicxulub, which is one of our case studies, we have a lot of studies that talk about inhomogeneous hydrothermal alterations. You can have these localized conduits and flow within the crater. And we know that life returned to the crater almost immediately post-impact in terms of our geologic scale, about 30,000 years. So we're interested in the longevity or the duration of the hydrothermal system and what temperatures those are at, so we can link to potential habitable places within a crater. So I'll talk about our workflow. First, we looked at the external morphology of the crater, or of the grains, using an SEM. We classified tentatively what the diffusion or what the shock microstructures would be. And then based on that, some of them went to diffusion experiments and some went to regular zircon helium dating. And I'll discuss this in the second part of my talk. Of the ones that went to the diffusion experiment, we then mounted them and looked at the internal structure of the grain using electron backscatter diffraction. So this is a way to look at misorientations within the crystal, characterized deformation. So a little bit of the nitty gritty, since we're looking at a lot of these Arrhenius plots. So we take a single one of these grains and perform a diffusion experiment on that, which entails packing it in a packet, pumping it down to ultra high vacuum in a cell, and then heating it up for a certain to a certain temperature, holding that for a certain amount of time, and then analyzing the gas. So one of our steps would look like this, and then we'd get gas. And so we're going to populate this plot here on the right. So it's inverse temperature and then a diffusivity term on the y-axis. So we step through heating up the crystal during our prograde path, and then we step down in a retrograde path. And what you'll notice here is that this sort of populates into a linear array. So volume diffusion obeys a linear relationship, as you can see on the bottom here, where the slope and the y-intercept are what we use to plug into the equation for our closure temperature. And the slope is proportional to the activation energy. So this should be pretty similar if we're dealing with the same material, zircon. And this frequency factor term, which has this A naught or A squared term. And this A squared is the diffusion domain. So it's the part of the grain that you're actually diffusing helium from. So just to keep in mind, we're looking at slope and y-intercepts for the plots that I'll show today. So we have a couple of possible outcomes that I'll go through so we can look for the patterns together in my slides and my results coming up. The first would be that we just have plastic dislocations or perhaps fractures that are not interconnected. And in that case, we are defining one slope and one y-intercept. In cases of higher shock pressures, shown here, either with planar deformation bands or a granular textured grain, we get these fast diffusion pathways out of the crystal, or these highways that helium can escape the crystal really easily from. So it's a reduction of the size of the domain that you're diffusing from. So you can envision helium getting out of this crystal quickly here, and not so much from the center of the grains. And in this case, you have similar slopes, but two different y-intercepts. So I'll quickly run through some of these Arrhenius plots. You can see this is a featureless grain from the Chicxulub, and that's confirmed with the EBSD image. We have the same slope for the prograde and the retrograde paths. And so this is indicative of one single domain. You're diffusing from the entire grain all at once. And our closure temperatures are within the accepted range. So it should be around 200 degrees Celsius. In the case of a grain that has planar deformation bands, you can see in green here, we have a couple of different best fit lines we can plot through the data with a rollover in between the first and second best fit lines. They have similar slopes, but very different y-intercepts. So this is indicative of multi-domain diffusion. You're diffusing out of the smaller domains, they degas first, and then a larger domain second. And our closure temperatures are again within that accepted range. Finally, this granular textured grain, these beautiful tiny little granules in a single zircon crystal, yields 2 best fit lines, similar slopes with a rollover in between, but 2 very different y-intercepts. So again, this is indicative of multi-domain diffusion. And here we get a closure temperature that's much lower than that 200 degrees Celsius mark. All right, so if we plot all of our slope data together, I'll just point out that the black points are from published literature from tectonic studies. And you can see that the no matter what the shock features are, we're within the similar range as the other grains from previous work. So pretty constant value that we can use there to plug in to our next term. So if we now look at the y-intercept term, we just looked at the slope, now we're looking at the y-intercept, we can see that there is a decrease in the domain size shown on the y-axis based on the shock features. So because of the shock, you're reducing the domain that you're diffusing out of, and you get a smaller size for the highly shocked material. And then finally, we can look at the closure temperature, which is what we're sort of interested in for habitability. This is the temperature at which this grain is passing through at a certain age. So if we get an age of a crystal, that would be the temperature that we're recording here. So basically what I'd like for y'all to take away is that if we look at these highly shocked grains, we have closure temperatures that are less than 100 degrees Celsius. And this is quite cool because we can use these smaller domains to record ages of less hot material. So now I'll talk about just our zircon ages that we have obtained. This is predominantly from the Ries impact crater, so it's the younger one in Germany. And what you can see here is that the least shocked grains are older than the most shocked grains. So each of these bars is a single zircon crystal, and they're colored by the shock textures. So lighter ones are the highly shocked grains. And if we just take a weighted mean age of the least shocked material, we get an age that's closer to the impact age within error of the impact age from the argon-argon constraints. And if we take a weighted mean age of just the highly shocked material, shown in this blue box here, we get an age that's almost 1 million years younger. So we can potentially extend the hydrothermal system duration for the Ries crater up to almost 1 million years. So in conclusion, we have impact-induced shock damage that affects how helium diffuses out of the grain, and the diffusion domain is the primary controller of that. So you must characterize your grain's deformation if you want to interpret the ages properly. So if you look at the least shocked grains, then you can potentially get an impact age and date, a crater that hasn't been dated before. Or if you're interested more in the habitability, hydrothermal system longevity, then you can look at the shocked grains that have variable domain sizes within them. And with that, I'll take any questions. Thank you.
Guess we can start. Are there any questions in the room?
I have a question.
Sure.
So in your plots, maybe you can both go back to, I guess any of these plots that show the inverse temperature on the bottom.
most efficient way. I know, I'm like,
Yeah.
Yeah.
So you never described the vertical axis, or maybe I didn't pay attention. Is E the diffusion coefficient?
so this is the diffusivity. This whole term is the diffusivity. So the diffusivity term relies on the domain size.
And how do you get the diffusivity? Because what you measure is, so you describe the step heating,
Yes,
and then what you measure is concentration of helium.
concentrate, yeah, the volume of helium. We use these certain parameters based on the total fractional loss of the grain. So you need to know how much helium was in the grain fully, and then you use, it's basically like partial differential equations that change.
How do you know how much helium was in the grain?
So you're asking about yeah, it's great. So at the end of the experiment, we put them in a different cell in our lab and lays at 1300 degrees Celsius for a certain number of minutes to fully degas the grain. So then we have like the total concentration that we can then calculate the fractional loss for. Yeah. Yeah, and the diffusion kinetics change depend on how much of helium has fully degassed. So you use 3 different equations. One is for less than 10% of the gas. One is for less than 80%. But those are all sort of nitty gritty details.
Okay, any other questions in the room? What about questions online, anybody?
Tim.
Yeah.
Yeah, I have a question. Can you go forward a couple slides?
What's Spanish?
Yeah, so if you go here and then compare this with your last plot, so you have closure temperature, and then you also have an age. So you talked about how, okay, if you take the 2 end members, you can get the hydrothermal age versus the crater age. Am I too optimistic in thinking you can also get the rate of cooling of the hydrothermal system, or is that in the noise?
I think that's within the noise, sadly.
If you had enough, like, is that within the noise of the technique, or if you had large enough sample volumes and enough zircons that you did this on, you know, given that I'm sure it's a really intense, you know, analytical technique, but like if you did have enough, could you plot closure temperature versus age and see some declining relationship?
Right, yeah, so I would say that it's partially the technique. So you would need to look at an impact crater that has a sort of extended hydrothermal system, because the zircon helium, or an old crater, because the zircon helium errors are about 8%.
Okay.
But if you characterize a lot of these grains, and you have 20 that are granular textured, highly shocked, and X number that are not shocked, then you could maybe do some comparisons of sort of statistically robust sample sets to try and get at some of the rates. You could also use different thermochronometers, so we can use the mineral apatite, or pairing this with a lot of the argon-argon work that's already been done is really good, because argon-argon also depends on the domain size, but generally has higher closure temperatures. So you could try and start to track using all the different thermochronometers through time.
Right.
Yeah.
Yeah, because both the rate and the sort of shape of the.
Right. Is it steep? Is it, are we looking in an area that just has high permeability and cooled off really quickly?
Right.
Yeah, it would be really interesting to do a cross comparison too, like across the crater, a couple of different sites.
Cool.
Yeah.
Okay, any further online questions?
Doesn't look like there are any right now.
Just so I can't
I
see
do,
hands.
but nobody's raised their hand.
Okay, nobody has, okay. Okay, so thank you, Kat, and I guess,
All right, well, our second speaker today is Evan Carnahan. I'm just going to mute you for a second, Evan. So I muted you. I got it. Yeah. So Evan's a graduate student in electrical and computer engineering at UT, and his background's in mathematics, and he works on a range of interdisciplinary computational problems, everything from glaciology to EEG signal processing to planetary science. Today we're going to hear Evan talk about material transport across ice shelves by sinking of impact generated melt chambers. So take it away, Evan. And you need to, yeah. You're still muted, Evan, so we can't hear you.
Cool. Can you hear me now?
Perfect.
We've all learned how to deal with a little bit.
Yeah, well, cool. Well, as Tim said, I want to talk about material transport across ice shelves by the sinking of impact generated melt chambers. So this will have some similar themes to what Kat was talking about, but from a different perspective, and we'll look at kind of the dynamics of the process, but a lot of the kind of elements that she touched on will be important. All right, so the focus of this presentation is going to be Europa. It's a moon of Jupiter, and it has, is this really yellow? Or are we? It's really yellow. All right.
It hadn't been earlier, so.
Yeah, that's on me. It's off. Oh.
Well, we like yellow.
Okay.
yeah, it was okay.
Yeah, it was okay. All right, cool.
Late night feel
Ambient.
Yeah, so anyway, so we'll talk about the icy moon of Europa, and kind of the important details to know is that has this kind of thick ice shell on the outside of it, and then what they believe is a subsurface ocean below it, and then a rocky interior. And kind of as our seeking out of where life is and our solar system has expanded from Mars to these other places, currently these icy ocean worlds present a really strong, or at least a potentially habitable environment in our solar system. And there's kind of an interesting contrast where there's a challenge and also kind of an exciting opportunity that there's this ocean that is covered by this thick outer ice shell that insulates it. And that provides a means for potentially those materials or exchange between the outer surface and that ocean would have to go through that ice shell. And then also a challenge of that is that that would actually have to happen. You'd actually have to have exchange between that outer surface and the interior ocean. And so what is going on in that ice shell can be kind of indicative of what we think the habitability of that subsurface ocean is. So I talked about potential transport through that ice shell, but why is that important? And so we thought that the rocky interior of Europa has serpentization processes and other things that can produce hydrogen. And one potential way that you can have life is if you can have energy from redox reactions. And so that kind of begs the question of where could these oxidants come from to supply these redox reactions in the subsurface ocean. And if we look on the plot on our right, this is kind of the estimated oxidant or oxidant fluxes that are at the surface of Europa here in purple. And then there's the estimates from hydrogen gas from crustal serpentization. And so it kind of begs this question of, okay, well, how would those oxidants potentially get into the subsurface ocean to supply redox reactions there? and what are these, the physics of this transfer process. And so that's what we'll investigate here. So a few different mechanisms have been proposed to do this type of transfer from the surface of Europa into the underlying ocean. One of them is just kind of classic subduction. We reason from thinking about Earth and we think, okay, well, maybe subductive processes could have occurred. There is some limited evidence of these subduction zones on Europa, but there's a lot of theoretical arguments and of why this wouldn't happen on Europa. And so that kind of led to this idea of, oh, well, if you formed a melt, then maybe that would drain with the surface oxidants from the outside of Europa. And then there's some surface features that suggest that there is melting in that near surface. One of these is these chaos terrains, and there's various other ones in the center here that are indicative of melt in the near surface. However, there's not really been an energetically consistent mechanism for forming those melts in the near surface. And so kind of then it moved on to, oh, well, you had an impact and it breached all the way through the ice shell. That would mix whatever was in the near surface into the ocean, and that would allow for this kind of redox reactions to occur in the near surface. So so anyway, the challenge of that hypothesis, though, is that there's really limited evidence for these full penetration impacts that occur on Europa. And so if we look here, this is the diameter and depth ratio of all of the impacts on Europa. And most of them here in black are these just kind of standard, crater forming impacts. And then there are these two lines here at the bottom right that are identified as these multi-ring basins that people have hypothesized as being these impacts that have gone all the way through the ice shell. However, these form just a small minority of all the total impacts that occur, and these kind of rare events might not be enough to sustain life within the underlying ice shell. But if we look at these craters, if we look at in black, these are these kind of simple craters that are we can see on the top right here, which are the if you just have an impact into a body that kind of fit with our standard understanding of what a crater should look like if it occurred on Earth. And then you can see in this rollover in this depth diameter and this kind of the circles with the dots in them and then the plus signs, but there's, as you have these larger craters, you have this increase in complexity in the crater signature. And so you get these disrupted central massifs where you have this collapsed central location within the crater that's shown in kind of this top center image we have. And then on the far left are these multi-ring basins that people think are these like very complex craters. And so it kind of leads this, okay, well, if there's a few potential locations where you could have full penetrating impacts, but there's a lot of impacts that don't result in that, but result in these kind of weird crater morphologies. What is kind of going on here? And so this question is, does there need to be this full penetration impact that Cox and Bauer found in order to allow for vertical transport to occur from the surface? Could these non-penetrating impacts that just form craters potentially lead to vertical transport on a much more regular scale and transport those surface oxidants? So here we'll look at a non-penetrating impact into an ice shell. So this is an ice sail simulation, and that's just an impact software. What we'll see is that over time, this impact will go for about an hour or so. And over time, what you'll see is that this kind of central red, all right, we'll get to watch it again. Anyway, it's a fun simulation, so there's worse things. But what we'll see is that it will end within hours, just because it's very computationally intensive to run these simulations. And then for fear of trying to show you with my cursor again, I'll just point to kind of the center location where, and just for context, on the left is temperature, and on the right is kind of brittle, is a measure of damage. And so we'll focus on the left here. And we'll see the cold near surface at 0 kilometers, and at -10, we'll see the bottom of that ice shell, about a 10-kilometer thick ice shell, which is near the melting point. And what you'll see is that that red in the bottom, which is the ocean from -10 to -20, is at the same color, or is the same color as this kind of central location right below the crater. And what that's showing is that there's this large amount of melting that occurs within the ice shell. And that location is fluidized throughout this process. But what is the fate of this melt pocket? The simulation runs for about a couple hours. In that time span, it just is stuck static in that location as it ends, and then we measure the crater diameters, and then your impact simulation's done. But that fate of that melt pocket is kind of unknown throughout the time. So what we look at is we look at a simulation that closely approximates this Mannanen crater on Europa. That crater can be seen here in the center of this image, and it has this kind of complex morphology that is hard to even register as a crater, but is one that,
Crater in that.
yeah, there's no crater in that. I can trace it.
Okay.
Yeah, that's supposedly the crater, and but it again, like you say, it's very messy, it's jumbled up. It's not this kind of clean craters that Kat was showing in her presentation. So, and maybe this process. So what we do is we say, okay, well, we're going to take the output of that impact simulation, and we're going to have the melt chamber there, and that's shown in yellow at the bottom as porosity here. So one porosity would be all melt, and you can see the ocean at 0 below 0 here. And then at the top is temperature. And what you see is this large thermal anomaly. It's not just that melt is produced, it's that the whole ice shell is warmed up in the location of the impact, just because of the dissipated energy from the impact there. And so what we'll do is we'll take a code that we developed, and we adapt it to these cylindrical coordinates, and we evolve it in this quasi 2D setting. And then what we'll observe is there'll be a competition that will occur between, you'll have a cold near surface that is trying to refreeze the liquid, and you'll have a dense melt. And so that's another distinction between Earth, is that the melt that's formed from the impact is then dense because it's ice and that's water. And that will be trying to sink within the near surface. And so we'll see which of these processes wins out in this kind of competition. This is again for that Mannanen crater. And what we'll see is that that melt pocket rapidly sinks within the ice shell and sinks to the ocean below. That transports on the order of about 20 plus cubic kilometers of melt from the near surface below that crater into the underlying ocean. So if we're thinking about that really disrupted crater that we saw, this could be one potential explanation for why that crater just looks like an absolute mess on the previous slide. So, okay, well, how much did that melt and how long did that take? So this is that same simulation, but shown here as a bunch of slices in time. Time 0 is when the impact happened, and time 1000 is when the simulation's roughly over. And what we'll see is that within about 500 years, and then in the bottom right corner here is the percentage of that initial impact chamber that drains in time, with the circles showing the different snapshots shown at the top. And again, the temperature at the top and porosity at the bottom. What we'll see over time is that that porosity, or that melt, rapidly sinks, and about 500 or even less years into about 250, 300 years in, you'll get a large volume of melt that enters into the ocean. And kind of another fascinating aspect of this is that when that melt reaches the ocean, it's formed a porous connection between the near surface and the underlying ocean. So not only could that melt transport the potential materials from the near surface into the ocean, it provides a connection for where, if you had ocean materials that were pressurized, they could potentially escape through such a conduit from the surface to the ocean. So, okay, so that's just one impact. That was Mannanen crater. Are there other impacts that we can use to get an idea of how frequently this process happens, and how robust is it to changes in the ice shell? There's a lot that we don't know about these ice shells. We don't know how thick they are. We have some estimates, but there's a range of estimates. Here, they've looked at impact simulations. This is again crater diameter and crater depth. plotted in black are the observed crater depths, or sorry, the observed craters on Europa. And then in red are the other colors. Those are the simulations carried out by these authors, Cox and Bauer. And so they provide a means for saying, okay, well, there's a bunch of different thickness to ice shells. So here they're concluding the ice shell is about, or the conductive lid is about 10 kilometers thick. And so, so basically all of these different, so we use these as different starting profiles for the ice shell. So this is for a 5 kilometer thick, you would get that kind of rollover in depth and diameter. For 40 kilometer thick, you would get that, you know, other rollover in depth and diameter. And so we use this kind of suite of impact simulations, and we evolve them forward in time, like we did the Mannanen crater simulation. So again, this is a different impact, and what we see is that over time, this impact also drains, and it drains, but it takes closer on the order of thousands of years to actually drain. And then if we look, this is another impact that generates a melt chamber. You can initially see it in the left-hand side, and it slowly sinks, and then it actually refreezes in about 25,000 years. So some sink, some don't. What does that tell us about this system? Do we have to actually run forward all of these craters to know which ones sink and which ones do not? So we come up with a criterion for vertical transport. And so in the impactors community, there's this idea of a maximum transient cavity depth. So during that impact simulation we were watching, there's a cavity depth that the impactor causes that is the maximum one that is going to occur throughout that impact process. So that's going to be the maximum transient cavity depth. And then the other important value is what is the ice shell thickness. So that's just going to be, in the previous simulation, that was 10 kilometers. That's going to be just the ice shell thickness. So if you divide those numbers for the Mannanen crater that we were looking at, you get a value of 0.82. You had an 8.2 kilometer transient cavity, and you had a 10 kilometer thick ice shell over that ocean. That results in this dimensional value of 0.82. And then if we look at, okay, well, what fraction of that actually drained? We said there was around 80%, and so you can see that up here in the red value for a 10 kilometer thick ice shell. And so anyway, so what we found was that if you have a ratio of a transient cavity depth that is greater than half the ice shell thickness, you will result in this vertical transport. And so this cutoff occurs at if we look in the plot on the right, that's the fraction of melt drained divided by the transient cavity depth divided by the ice thickness. And so this occurs for all ice shell thicknesses. So it doesn't matter if you have a 10 kilometer thick ice shell or 40 kilometer thick ice shell. If you have an impact that results in that has a transient cavity depth of half the ice shell thickness, you'll result in transport from the surface into that underlying ocean. And so so that gives us this kind of criterion where we can use that to say, okay, well, we have all these crater diameters on Europa. Can we use those then to estimate whether they have a transient cavity depth that is more than half the ice shell thickness, and then determine whether those ice shells or those impacts led to vertical transport within the ice shell. So we kind of come back to this habitability question, and we ask, are oxidants entrained into this melt chambers that occur after these impacts, and could they really transport material? And so if we take a surface oxidant of 10 to the 14, 10 to the 18, should be moles here, and a mean surface age of about 40 to 90 million years, and we have to make some assumption about how thick the ice shell is. So just for this calculation, we assume a 10 kilometer thick ice shell. And so we scale what the final crater diameters are on Europa to transient cavity depths. And then we say, okay, well, did that actually lead to the sinking of this melt pot to the ocean? And then we have to make some assumption about how many oxidants from the impact actually survive that impact, because it's a highly compressive process. It's really intense temperatures. Anyway, and so we assume that just a ballpark around 50% of the oxidants within the crater are actually entrained into the melt chamber. And this results in a 1.5 times or 5 times 10 to the 5th kilograms per year. We'll see it on the next slide of transport. from impacts and the foundering of that melt pocket, or the sinking of that melt pocket. So to put that in context, if you look at Earth, from trees and other vegetation, you have about 10 to the 15th in terms of oxygen produced on Earth. And impact foundering is about 10 orders of magnitude lower than that on Europa. So it's a small fraction of that. And then the two other processes we talked about were, subduction or crustal overturn, and then the chaos drainage, or drainage of melts from the near surface. And those both provide larger amounts of oxidant delivery. But they have this challenge where we don't really know how the melts from chaos formation would form. That's energetically very challenging. And same with crustal overturn, is the dynamics of that process. And there's many good theoretical arguments against that happening. And so this kind of leads where you have impact foundering is this energetically self-consistent. You know what that perturbation is to the ice shell that causes the melt. It's the impact. And so allows for a kind of nice process that's energetically self-consistent to allow for the habitability or potential habitability of the sub-ice ocean. So yeah, so just in conclusion, impacts that do not breach the ice shell still result in this vertical transport on Europa, and a much larger range of impacts you don't have to penetrate through result in this surface to ocean exchange than previously thought. A few last points is that the drainage of impact melts below these craters has this potential to really change their morphology and aren't currently included in the interpretation of the morphology. And so one kind of interesting potential avenue of future work is how does that removal of something like 20 kilometers or cubic kilometers of volume from below a crater, how would that affect the crater morphology and lead to this kind of complex craters? And then finally, vertical transport of melt with entrained surface materials. It's this kind of habitability promoting process, and it's energetically self-consistent. And we investigate this for Europa, but it happens for conductive ice shelves between 10 and 40 kilometers. So it really could happen on Titan, Ganymede, Enceladus, some of these other ocean worlds that people have done a ton of head scratching about why they have these strange, complex crater morphologies. So I'd like to thank the CPSH for giving me funding for this research. It really, it's the only reason it really got done. And so thank you. And thanks to Mark for helping me with it.
We have questions here in the room.
Yeah, that was great. I guess I have a couple of questions. One is, it looks like, so I like how you're doing with transient cater depth, but the other way to look at it is the size of the upwarping of the ice water interface. Right, what would be the cross mantle interface on the moon and makes mascons or whatever. Yeah, and you could see that the one that didn't, in your 3 simulations you showed, the one that doesn't start with an uplift beginning is the one that doesn't make it, and the other 2 does. And maybe that may just be the consequence of the same thing. It'd be worth looking at it from the bottom as opposed from the top and just see it.
Yeah, so you're talking about
Right there, go back. Yeah, that one. See,
oh,
starting
yeah.
with a significant, and that's just a consequence of the bigger
Rebound.
Yeah. It has a preserved rebound, which in this case is water.
Totally.
Right? So
Totally.
anyway, that's an interesting. I guess I'm curious to attack it from the other side.
Yeah, we looked at a few different kind of, okay, well, what quantity is really controlling this drainage? And one kind of interesting thing is you can see that this impact, we thought first it could be like the depth that the melt pocket actually reaches. And here it's around 4 kilometers.
Yeah.
But if you go to this next one, it's actually below, it's like closer to 5. So it's really not that's controlling it.
At the bottom.
Yeah. And so there's no, crustal uplift. We thought about energy, like, was it the energy of the impact compared to what's, the energy in the ice shell? And anyway, so this was just one way of looking at it, but I think you're right. There could be a lot of these cutoffs.
Yeah.
And
The other thing I guess would be really interesting to do, and I don't know if you've looked at this, is that same question: the transient crater depth of the height of the rebound relative to the complexity of the morphology.
Yeah. Yeah, no, I haven't. And it's been kind of, our simulations are in too coarse a grid to really resolve any like morphological changes. But it is really suggestive when you're like moving this amount of material from below a crater that we're actually getting a little pushback from a reviewer right now who's saying like, how do you know it changes crater morphology? Well, we're like, you just removed 20 kilometers of melt from that location. So yeah, I think it would be interesting, to resolve that boundary. And I think probably there are computational or modeling tools to do that. So
Cool.
yeah, no, thank you.
Okay, I have a naive astronomer question.
Please,
This
yeah.
slide just before the conclusions.
Absolutely.
I must have missed something in there. Because
Yeah.
you have upstream delivery rate in kilograms per year.
Yeah.
I was wondering how the time dimension came onto that. Are you assuming a impact rate or something?
Yeah, absolutely. And so it's assuming a resurfacing rate. And so a mean surface age of about this. So it's saying that this many craters have occurred during that time, but there's kind of a circular element to it where it's like they determine that age by determining how many impacts have occurred, right? They're like, you gotta, and so they use the number of impacts to say, okay, well, given a lot of calculations that I'm sure you understand better than I, how old is the age of the surface we're looking at? But one kind of encouraging thing from this work's perspective is that is such a regular process that they can they can measure the surface age from it. So if it's that regular of a process, then it's that regular of a process for this melt drainage and these kind of habitability promoting processes to occur on.
Okay, I see we have an online question from Larry Trafton. So Larry, please go ahead.
Yeah, how important is the changing potential energy of the descending melt to keeping that melted?
Can you type it? I'm sorry, we're having audio issues.
Yeah, there's audio issues here for the online speakers. So if you could type that into the chat, then we could look at it, Larry.
Okay.
I have a question in the meantime.
For sure.
Did you look at how fast the oxygen delivery rate drops off of the bigger ice shell?
No, but
Because you just made a law for that.
what'd you say? Just
That's a rule, right?
yeah.
For any ice shell thickness, but not the delivery rate presumably drops off pretty fast.
Yeah. So like if you had a thicker ice shell, then a smaller fraction of the craters that you see on Europa would actually result in transport. And so for us, assuming a 10-kilometer thick conductive lid, that I would say like that's an upper to middle bound on that thickness or estimate, just because if you have a much thicker ice shell, then you're going to have convective processes that occur, and then your conductive lid will be smaller again. But so probably like a complete upper bound would be like 15 kilometers. But we just took 10 because that fit with Rona's like rollover estimation that we saw on the previous or a while ago. There we go. That rollover of impacts matches the black from Europa and the red from their simulations matches about a 10-kilometer thick conductive lid. So you would get a different estimate for a different lid thickness.
Okay, we got Mary's question here.
Please, can you?
Yeah, it says, how important is the changing gravitational potential energy to heating the descending melt, keeping it melted?
Yeah. So there's, I think that if I would suppose that probably, Larry, you work on really big objects, because there is some changes in gravity, and there's even some changes in melting temperature with pressure. But for these kind of smaller objects, that change in melting temperature is important as you go to, say, a Titan-sized object. But I've never actually heard of anybody doing changes with gravity. I think that in that there are many other factors, like we're not really sure how thick the ice shell is, or even like the grain size of the ice. But I hope probably as those things become more constraining something like that might influence our results or even general results on ice shell dynamics. But I haven't seen anybody have a changing depth gravity thing for ice shells before.
Okay, we have another online question from Chai-Long Ren. How do the tidal activities interact with the melt sinking?
Yeah. It's a good question. So the one kind of component that I glossed over in this was that there are these kind of heating processes that are even expected to maintain that why there's an ocean, basically these tidal energies as you have a moon orbiting as it anyway, and so you have this kind of squeezing or stretching of the ice shell that's maximized at the melting temperature of the ice shell. So that was just context. So for this process, the any increased heat into that domain. So we run these simulations without any tidal heating. Any increased heating into that would increase the preservation of melt, and thus how robust this was, or how frequently this transfer process occurred. And so, so that's how tidal heating would influence it, and it would likely just make this a more frequent process in Europa's history. But
You've got to calculate a minimum.
a minimum, yeah, and in many ways, yeah. I mean, there's even more conservative assumptions. Like, I mean, we fill in the bottom portion, that rebound that you're referring to, with ice, just to keep it on rectangular domain and stuff like that. And so our results are kind of a conservative estimate on how frequently this process would occur. But it hasn't been considered before, so we wanted to just make sure it was robust, and we were making these kind of conservative assumptions in showing that it exists. So.
Okay, thanks. Any more questions?
Was one more, or do you know three? More chat.
They're all right.
No, they're all those. Great. Okay, so thank you, Evan.
Yeah,
So,
thank you. Appreciate the time.